It was a spam call too, I think.
Yeah.
Okay, so back to the problem. I'll put Ka2 there, that says Ka2, 6.4 times 10 to the minus 8. Based on this value of Ka, can we make the assumption that x is much smaller than 0.0328? We can, and we will. We'll make the assumption that you can ignore plus x and we can ignore minus x. Which means that it's now just 0.0328 over 0.0328 times x. Which just equals x. Anyway, I know it says it over there, but I wanted to stage it over here in blue. That is a molarity. And that is our concentration of sulfide. There were two steps there. Let me revisit them. We ignored these two x's because they were small. Then we just said 1 over, or whatever this number is, it's on the top and the bottom, so we can cancel it out as well. Done. Based on the size of x, could we ignore it when compared to the other bigger number? We sure could. Done. Any questions about this? Aaron? How do we know we were trying to find the SO3 2 minus? Well, good question. It does say all species, and if this were your homework or an exam, it would say those species include those listed there. So you would, yes, you would. And what you would do is at the end of the first ice table, you still wouldn't have the sulfide ion. So that would be your clue that you have to do a second ice table. Logan?
The question asks for the pH of all species.
Oh, I'm sorry. The pH. Thank you. pH and concentration. I'm sorry about that. Thank you. And concentration of all species. Oh, so we still haven't done pH. Let's do pH now. Once we have the concentration of hydronium of 0.0328, we can find the pH. pH equals negative log of concentration of hydronium. And the pH.
We're just ignoring the second step because it's so small, right?
Question, so why are we ignoring the plus x and minus x? Yes, because they're so small.
We can calculate pH as well, correct? Because we're adding some hydronium, but it's completely invisible.
Right, what we found out is that the x here is 10 to the minus 8, which wouldn't even show up on this. So yes, we are ignoring it. I'll make that note, ignoring the hydronium from second ice table because it's insignificant. Angel?
What would be like that in most cases for dichotic equation for it to be same as the Ka the conjugate?
So question, when you get down to here, will the concentration of this ion be equal to Ka2? Typically, the answer is sometimes. Yeah. So, but to know for sure, you have to do the whole thing.
Okay, when it's that small, would it
So,
be the case?
well, let's think about why this happened. So what happened was we had zeros up here. That means that we generated the same amount here. And that's why these numbers were the same. That often will happen, but what I will suggest to you is that you always have to solve it to be sure. So, and the short answer is I can think of cases where they may not be the same. Many times they are though, so it's a good point. Mackenzie? And then Hannah?
So we did the two tables because it's a polyprotic acid, so it's kind of like it takes 2 steps for it to ionize completely or something, right?
Yes.
But if you gave us just like calculate the pH of this, would we know that it's, would you tell us that it's a polyprotic acid? So if we were to do two.
Good question. So if the question was, calculate the pH of this, even, and it's polyprotic, and if you were to do one ice table, could you get the right answer? Is that, or, I mean, the answer is yes, because in this particular case, you make all of your hydronium in your first ice table, and you make an insignificant amount.
I mean, like, do you expect us to know that's polyprotic if you're looking at it? If you give us.
Oh, do I expect you to know that this is polyprotic?
Yeah, or would you tell us in the problem?
I expect you to know that this is polyprotic. Yeah.
But we have a Ka1 and a Ka2, so we would know.
You would also know it's polyprotic because you're going to look up the Ka value from your conversion equation sheets. And you'd be like, oh, there's 2 of them. So yeah, there is reinforcement there. Yeah. But pretty much, yeah, you would have to know that that's polyprotic. Sorry, Hannah and then Kate.
Can you reiterate why? So I understand most of the hydronium was reactive in the first ice table.
Mm-hmm.
So then, if we were to, because it's still a product on the second ice table, why do we bring down the concentration, equilibrium concentration into the second ice table? And
Good.
why would we just keep it at 0 and run it through and get the same answer?
Good question. So your question is, why did we bring this value down to our second ice table? And if we didn't, would we get the same answer? And what's happening, and this happened on homework too, I think on the last problem, that was sort of our demonstration problem for this, because we were dealing with H3PO4. And in that problem, and this is very true, whatever you generate from your first ice table, you need in your second ice table. So if you see hydronium here, no matter where it shows up down here, you have to include it.
Okay.
Because our process is this. We see that this is the largest K value, Ka, Kb, Kc, what have you. This is an acid, so they're all Ks. So we work through an ice table for our largest value of the equilibrium constant. I've already spelled K first. And then the next largest would be next. And then the next largest would be third. And I've said this before, and it's sort of underneath everything that we do, but this pH is our third ice table. Because that is H2O plus H2O goes to hydronium plus hydroxide. That's what underlies that. And that Kw is 1.0 times 10 to the minus 14. So technically we're doing that last. And our process went like this. Make some hydronium, see if we're going to make any more hydronium. Turns out we're not. Then do pH last. And maybe I was being a good instructor, maybe I was being a bad instructor by forgetting pH till the end. I forgot totally. But that's when you're supposed to do pH, is at the end.
So you can say ignore hydronium from second table because it's insignificant, like the amount of it.
Because, right, but the process is good. Always go through both of them, just in case. Kate, question?
So pH goes from the hydronium and then H2SO3. What about H2SO3 and then SO3? The pH, we have to do pH for those?
Oh, are we not? So if your question is, how do we do pH for this? Think of it as, we started with H2SO3. And it had the largest K value, was a K1. We made some hydronium. There's a K2, which could make more hydronium. Let's check it out. We do the second ice table. We put an X right here for more hydronium. We find out that more hydronium is so tiny that we don't need to count it. So we went through the process to see if it counted. I will tell you this, and I don't have an example right now, but when we do the same process for sulfuric acid, the second ice table does matter. And it does, your X in your second ice table for sulfuric acid does add, or does change the pH. Anyway, but
So we'll just solve the pH, just the one something.
so we solved pH based on this number because the additional hydronium that we add right here was times 10 to the minus 8, so it didn't change the 0.032. Good question.
What about for the H2SO3? Yeah, like 0.0672. Yeah.
What about, so what about,
Why wouldn't we,
why wouldn't we account for the hydronium made by this? We just did.
I think the confusion is just in the writing of the question again. That
Oh.
They're trying to calculate pH of all species. Which is
Oh,
yeah.
sorry. And this is totally my fault, and I apologize. So the question should be, calculate the pH. And the concentration of all species. Dot, dot, dot. So, yes, no, my apologies. There is only one pH. That pH collects all the hydronium from all the sources. Yes.
Okay.
And what's weird here, aside from my very poorly and confusingly worded question, which is just wrong. Thank you. That's the. But there is only one pH, and but you can get hydronium from more than one place. But you all add it up and then do pH. Yeah. Thank you. I am happy to say that the way the class is structured, we have enough time to figure out all my mistakes and then make them make sense. But these were all good questions regardless. Other questions? Okay.
So in like 6.4, like times 10 to like the negative third, you wouldn't have to solve pH because it's smaller than K1.
If this was a -3 by the time you got to this x, you would have to add it in, and then whatever you got total, you would use to find the pH. And that is what happens if you do something like the same process for sulfuric acid. Cool. Okay, very good. No, and what I really appreciate, again, I apologize for the mistake, but we worked through it all. Hopefully we feel better and it makes sense now. And that is very good. But in the meantime, let's continue. So trends in acid strength, we will focus on the oxyacids. What I mean by that is if you read your textbook, there's one or two other trends that we will not focus on. So these are the ones that I would say are more important and that you're more likely to see as you move on. the oxyacids. When the oxygen is attached to another element, the acidity will depend on the electronegativity of the element attached to the oxygen, which we call Y. So if I then attach Y to oxygen, and you can see that Y is going to be chlorine, bromine, and iodine. And we look at both the electronegativity and the Ka values. We see that as you go down, it goes from -11 to -9 to -8. Larger Ka values mean stronger acids. So of these three, hypochlorous acid, HOCl, is the strongest. And the first thing I will say is if you have any questions about acid trends, you have a sheet that has all the Ka values on it, and you can look up what the trend is. You will be given that on each of your, so you won't have the Ka sheet for your first exam, but afterwards you will for the next time. Good. Then the idea here is the more electronegative this element is, the more it is going to pull the bonding electrons away. My abbreviation for electronegative is capital E, capital N. Right, and the definition of electronegativity, ability to pull bonding electrons towards itself. More electronegative pulls the bonding electrons towards itself. And when you pull electrons from this bond towards the Y atom, it actually pulls some of these electrons over as well, weakening this bond. That's what we're seeing here. So more electronegative pulls bonding electrons towards itself, which weakens the OH bond. Weaker OH bonds makes it easier to release an H plus and makes it more acidic. Weaker OH bonds, or a weaker OH bond makes it easier to break and easier to release an H plus. And if it's easier to release an H plus, it's a stronger acid. One other trend. More oxyacids. Oxyacids, this time with multiple oxygen atoms. Electronegative oxygen atom. Atoms draw electron density away from the H. Let's see. From the OH bond. Here we have perchloric, chloric, chlorous, and hypochlorous acids. As we go this time up, we see that the Ka values get larger Ka values. Mean stronger acids. Quick question, quick check-in. Of these acids, which ones are considered weak acids based on their Ka values? For certain, these two are weak acids. This one, well, is sort of right on the cusp, and this one's definitely a strong acid. So, weak acid. And this one just, its Ka value is strong. This time our picture here is that we have oxygens pulling electron density away from chlorine. Pull, well, I use the term electron density. Pull the bonding electrons, that's another way of saying it, pulls bonding electrons away from the chlorine towards the oxygen. Pulls bonding electrons. Then the Cl will pull bonding electrons away from the O. Which weakens the OH bond. Question, Lois?
Is it oxygen considered
So these oxygens pull bonding electrons away from the chlorine. This chlorine pulls bonding electrons away from the O. And so you can think of, like, in my head, the atom next to the OH bond can pull electrons away and make it less, make it a stronger acid. Now, two atoms away can pull. And so what we're seeing is that what makes an acid strong and weak is the bonding of the atoms around it. So does that answer your question? Oh. Oh, yes, that's the one that should be an O. So, from OH bond, which weakens the OH bond. I think it'd also be right to say it pulls electrons or bonding electrons away from the O as well, but certainly not the C. Oh, now let's answer this question. Which is more acidic? By acidic, I mean stronger acid. Which is a stronger acid? In this particular case, we have the C double bond OH group. So the OH that we're talking about is, the H is right there. What I'm suggesting is that these chlorines will pull electron density and that this is the stronger acid. And that is what seems to be true. And in this particular case, we have the OH bond down here, 1, 2, 3 atoms away, affecting the strength of the acid. Final topic of this chapter, Lewis acids and bases. This is, Lewis acids and bases are the most general definitions of acids and bases. A Lewis acid is an electron pair acceptor. It must have ability to accept electrons. A Lewis base is an electron pair donor. Now, let's revisit the Kb reaction for ammonia. And we've had in this chapter already Bronsted-Lowry theory of acids and bases. Bronsted-Lowry theory says that in H plus a proton moves from H2O to NH3. But now we're going to cast it in terms of electrons. And as these theories of bases and acids get broader and broader, one thing to remember is that everything we know to be a base or an acid before, for example, do we know that ammonia is a base? We have known that since last semester. And last semester I said, remember it's a base because I told you so. And then this semester we saw that NH3 could accept a proton. Now what we're going to see is we're going to start thinking about acids and bases in terms of the electrons. And this is something that you will do all the time should you be fortunate enough or unfortunate enough to be taking organic chemistry in the future. But now we're going to think of it as this electron pair being donated ammonia is a base. We knew ammonia was a base. Nobody's changing teams. We just have a bigger team now. Now that pair of electrons is going to form a bond with this H. How many bonds does hydrogen want? 1. Still always true. That means that these two electrons have to go over to the O. And so these electrons form a bond. We are making NH4 plus. Like so. These are not done, but at least they show all the bonds. What's the charge on NH4? It is plus. It is ammonium ion. Let's go back and do formal charge analysis. If we did, we'd find that plus is on the nitrogen. And if we did, we would find this oxygen to be negative. And our products. Are the same dang products we got for Bronsted-Lowry theory, but now we're thinking of the reaction in terms of electron pair movements instead. And we could do the same thing backwards. Well, let's see. Base, let's call this a Lewis base. Lewis acid. On the product side, since the reaction can go in reverse as well, take a pair of electrons, move them sort of in the opposite directions, and we end up with ammonia and water. Lewis base for hydroxide. Questions about this? It will turn out that when you get to organic chemistry, a lot more things will have electron pairs moving than protons. And so right away, when you get to organic chemistry, you'll see things that don't have hydrogens attached to them that you'll be able to use this theory. A couple of additional examples. Here we have ammonia plus boron trifluoride forming a bond. We have the donation of an electron pair to boron, which does not have an octet, to complete its octet. We talked about cations as Lewis acids. We have a cobalt with 6 ammonias in the pictures here forming bonds with cobalts. And this species in particular is called a complex ion. And I think we talk about that in chapter 20 or so in this book. But we'll come back to that. With that, I believe it's the end of chapter 16, and with only 5 minutes left, that seems like a very appropriate place to stop. Oh, well, we have companion problems, but they're companion problems.